Right, we've now got our 3 moulds all sitting there ready to go. Pouring basin over here, feeder extensions over here, and the bottom end of the big core that we made earlier. When we pour it, keep an eye on that big end of the core, because you'll be surprised how much liquid and gas comes out all these little holes. Well, we'll now see if we can light up and see how we go. Blower. Fire the hole! No fire in the hole. Turned it down too low. Sorry? I turned it down too low, and it needs to get a bit... That's better. Now we wait about 45 minutes. So over here, 670, that'll about do us. A little bit warm, but by the time we get it there, that'll be pretty good. Okay, remove the degassing shield, if you wouldn't mind, young lad. And turn it off? Yeah, turn it off there, and turn off the other one, the little one on the thing there as well. Yep. Make certain you get them both. Yep. Righto. Where's the XO? The XO is here. I'll put the XO on. I can probably manage that. You're right. Yep. Up we go, Ace. Now we want down a bit, please. Down a bit down the back of the basin. There we go. Wow, that's taken it fast, that sprue. Wow. Boy, that's handling metal. Sheesh, too big, Hayden, that sprue. It's slowing down now. Whoop. Whoops, daisy. Yeah, I can see. I can see that. Don't worry about it. It's probably stopped now. Next, Hayden. Boy, that goes fast. That sprue's way too big. I can't pour it hard enough to fill that. How are we going? We're just about there. I don't know whether it'll light, so watch it. There we go. Yes, it is. I won't take all of the mould, I'll take the top. Alright. Come on. Sugar. Gotcha. Now I got crap here I want to get rid of if I can. I should have kept it before. I need to get rid of that stuff. Righto. Hey! I'll leave that one there for the moment. We'll just temporarily move this while we do the same with this bludger. And up. Come on. You can see the fill lines up, the flow lines up here. Water. Okay. Filter down the bottom, runner, that looks quite good. Yeah. And does that crosshatch pattern work beautifully? That is absolutely brilliant. Look at that. That's magnificent. That really is quite something. That lovely. Well, we learned something today. Something worth knowing.
Yeah, I saw it when you flipped it.
Yeah. All right, we've got our 3 pistons now out of the sand and all ready for degating. In fact, I have degated one of them. I thought maybe we'd have a little bit of a post-casting conference, as it were, on the gating system we've used and the alloy we've used and what it's like to cast with. The alloy we in Australia call 319. In America it's probably close to 336, I think it is. It's a eutectic silicon alloy containing around about 12% silicon. It's got significant amounts of nickel, copper and magnesium in it, and these altogether render it a heat treatable alloy, and I will be heat treating these. I'll be giving them a T5 heat treatment, which will be 8 hours at around 200 centigrade. The nickel also confers some higher ability with temperature than you might expect with aluminium alloys, making it an alloy most suitable for use as a piston. It's also very wear resisting. It would make good pulleys, for example, too. Now, we cast 4 kilos to get each one of these, and the piston itself weighs 1,690 grams, so the yield's not exactly great. We did, in fact, in an earlier one, use the side risers as a complete round like this one, and we decided that the yield then was even worse. It was a bit unnecessary, so we've ripped a bit off the risers on this one, the bit off the feeders. The only danger with that is that, as you can see, this alloy is renowned for very high shrinkage. It's a centerline sort of a feeder, but it's a bit messy, and this one cut off an earlier piston. I have slit, roughly polished, and then etched in caustic to bring the porosity out. The only danger, of course, is that the porosity moves like this into the piston. And this was a bit of a worry when we cut them down like this. But this is the one I've cut off, and I've just quickly polished those up, linished them up. There's no sign of any porosity there at all. I think these will be a rather excellent piston. We have in particular chilled the bottom, and normally when you cast metal against a chill, it tends to come out a bit ordinary. You get sort of flow lines in it, and the flow lines can even trap a bit of air or gas, and you sometimes have to take quite a bit off the casting to get that to clean up. But I'd noticed that Japanese castings, automotive castings, cylinder heads, that sort of stuff, engine blocks, often have this cross-hatched pattern on them, which I wondered what it was for, and I thought, well, I'll try it on the little chills we used, and it's brilliant. It absolutely produces the best looking finish on the bottom absolutely possible. There's no problems there with lack of flow at all, and no problems there with trapped air. I think these pistons will be very, very solid, and they'll only need the slightest lick to get down to the really good metal underneath. Now, we decided to do this with what we believe to be the best sort of gating system possible. We have here a decent pouring basin with a ridge, a tapered sprue. It's a slot sprue in this case. We chose a slot because that gives increased friction and will help slow the metal down more. Secondly, it also mates well with the filter that we put in the bottom of the mould, which you can see now sitting here in the metal. The filter, as I said before, it's not really to clean the metal. It does a bit of that, sure, but its main purpose is to slow the metal down. At the bottom of this sprue, the metal will be doing pretty close to 2 meters a second. Now, you really shouldn't pour metal into a mould any faster than about 0.5 meter a second, but it's very hard to get to that 0.5 meter, to get down that low. I mean, you can get away with about 1 meter a second, but you know, really the 0.5 meter's desired. So what the filter will do is slow that 2 meters a second down by a factor of 4 or 5 to hopefully 0.5 meter a second. And we've deliberately made this runner bar in total 4 times the area at the base here of the sprue. So the velocity in here, the metal velocity here, should only be 0.5 meter a second. Then it goes into the 2 feeders. Any air that does get pulled down, and when you first start a pour, you're always going to get a little bit of air pulled down, will go into the feeders and come straight up the feeders. They won't go into the casting, and they won't damage the casting. So in that way, we hope that this gating system is giving us the best possible casting. This sprue, and you may have noticed when I poured, I commented that I really couldn't keep this pouring basin full because we figured the sprue was a bit big. It took 14 seconds to fill this casting, and if you calculate the flow down the sprue, it should have hit the bottom at, as I say, 2 meters a second, and with that area, that would give us about 600 grams of metal passing there every second. Now, that's an initial flow rate when you first start to pour. As the casting fills up, of course, the head between here and wherever the metal is gets less and less, so the flow slows down, and that plus the friction that you get here tends to halve that value on average. So we would get about 300 grams a second from start to finish of the pour, and 300 times 14 seconds comes out almost exactly at what we got, the 4 kilos weight. So that worked quite well, but we feel that was a bit quick, and that we want a flow rate, a fill time more like 20 seconds, because this is a very fluid alloy, and even though it's being poured very cold, it's quite thick, and we figure we can get a slower time. And the old adage of pour as slow as you can is always a good idea. So we will probably cut this sprue, which at the moment's just under 6 millimeter thick by nearly 22 wide. We'll probably cut that down to about 3.5 millimetre thick, and cut it down all over its length by that amount, by 1.5 millimetres, 2 millimetres, that sort of thing. Well, I'll cut the rest of them off, and we will get them into the oven, get them heat treated, and the customer can come and pay me for them, which would be nice. One of the more common issues raised in the comments to the first 3 parts of this video series has been, why not just CNC machine the piston out of billet? So I thought I'd devote a few minutes to discussing that issue. A couple of initial thoughts. The customer requested a cast piston, so we made him a cast piston. And in the billet versus ingot debate, we need to acknowledge that both actually start out as liquid aluminium, i.e. both are initially cast. Now, while casting is my thing, I am not totally biased against CNC. I own a CNC mill, and I have used it to produce things rather like the complicated 9-piece die for this particular casting. It's a 4-barrel throttle body. This one's been lying around for a while, so it's got a bit dirty now. And this is an interesting case in point, because we've used CNC machining to produce an iron die. Then we've used the iron die to produce quite a nice looking casting. And then we've gone back to the CNC to finish machine that casting off. This is an excellent combination of the 2 technologies. I mean, we could have just nibbled this whole thing out of a huge lump of billet. And there are people who sell 4-barrel throttle bodies that are made that way, but they don't look anywhere near as nice as this one. Believe me, the ones I've seen, they're chunky, horrible, heavy, hard-looking pieces of rubbish, I think, anyway. Now, at first I decided that this piston couldn't be made by CNC because you couldn't get billet in a piston alloy. However, it does look as though alloy 4032, which is used by Mahle for pistons, and it happens to be very close to the 319 alloy that I used, and in the US that 319 is called 316. It is available in bar stock, although not here in Australia, it would seem. I'm not sure you can get it in the necessary 105mm diameter though to make this piston. This is fairly large. The main impediment to machining is that the inside of this piston has to be machined 100mm deep through a 90mm hole opening, and all while you're dodging around these gudgeon pin bosses. The difficulty is in getting tools to cut under the gudgeon pin area, and if we look at the core box we can get a better look at it. I mean, we've got to cut this area down in here. Now we can cut around here with a thin enough tool, and we can probably get down to about there before the tool begins to smack the edge of the piston. But how do we cut around here? This is where it becomes very, very difficult to do. And I've spoken to a couple of CNC people, and they tell me that, yeah, it can be done all right. But the first thing they say is that, oh, yeah, well, but we'd probably have to fill this in here, sort of in some sort of wasted way, a bit like this. Let's mark that with a texter so you can see it. They'd sort of fill it in, maybe a little like this under here, so that all of this area was sort of filled in and solid, and then they figure they can sort of sneak a tool down here like this, and cut this area out, and they get even wasted away a bit under here as well. Sure, you could do that, but that's not the part we wanted cast. So that's an admission that this particular piston cannot be made by CNC. Now, apart from that, when I said to them, well, we only want 7 parts, they said, look, the required drawing, programming, toolpath determination, the special tools you'd need, the probability that you're going to need some sort of jigging would all add up to prohibitive setup costs. Then a slug of billet to make that, we reckon is about $60. And then you've got the machine runtime. This led to a guesstimate of around $1,500 a piston. This is way more than the $200 that we should have but didn't charge. And all I can say here is that if anyone thinks they can do better, please give us a quote. If we give you an old piston, because that's all we started with, make a piston using the 4032 alloy and see if you can do it for under $200 each. I don't reckon you can. Now, the other point that comes to mind is that, to the best of my knowledge, no one is regularly making pistons by CNC. If doing so was better, cheaper, quicker, easier, etc., then it would be common practice, probably at OE, aftermarket and restoration levels, but it doesn't seem to be done at any of these. And this despite that modern pistons are only about half the height, so instead of having to come in from here with your tooling right from the top, you've only got to come in from about there, and it would make it an awful lot easier. But nobody still seems to be doing it. The other thing is that if you make pistons in reasonable quantity, you do it in a gravity die, and you could cast a blank ready to be machined with the inside complete about every 1 to 2 minutes. Now, I could do this here with the die, which maybe it'd be about $3,000 worth. And I'd only use a few $100 worth of equipment that I already have. And as I say, every 1 to 2 minutes, I'd bang out a piston. I don't need a $100,000 plus 5-axis CNC mill to do it. Now, the other thing is that, to be honest, I find this habit that seems to be developing of reaching for a CNC mill as the first way of making something rather concerning. Such machines are often used to turn lots of good aluminium into swarf, and that's known as chips in the US, I believe. Known often as frozen electricity, aluminium is an environmentally expensive resource. Should we not think twice before turning most of a good lump of it into useless swarf, which is lossy to recycle and always produces a contaminated, lower grade material? I ain't no rabid tree-hugging greenie. No foundryman is. But then one thing we foundrymen can do to ease environmental strain is to produce a casting to near net shape. This minimises wastage during and indeed the time spent on any subsequent machining. And this is what we have done by casting this piston. Now, as a final note, may I say that I find great personal satisfaction in creating something with my own hands, particularly while I'm using age-old technology, assisted maybe a little by largely self-made rudimentary equipment. That with practice and patience I become able to do so at an engineering and aesthetic standard that has people paying money for my work greatly increases that satisfaction. To be doing it with that most primal of forces, fire, is just wondrous icing on the cake. And to me it's just so much better than doing a drawing, feeding it through a bit of software and pushing a big green button.